All right. Well, welcome everyone. I am very happy to be introducing James Finley as speaker for this month's Shrier Family Topics in Rehabilitation Sciences seminar. Dr. Finley received his BSc in Mechanical Engineering from Florida A&M University and his MS and PhD in Biomedical Engineering at Northwestern. After completing his PhD, Dr. Finley completed a postdoctoral fellowship in the Department of Neuroscience at Johns Hopkins University. And since then, Dr. Finley, he's currently an associate professor in the Division of Biokinesiology and Physical Therapy at the University of Southern California, where he directs the Locomotor Control Lab. So James's primary research interest is in understanding how walking is controlled and adapted in both healthy individuals and in individuals with neuromotor impairments. His work is, I think, really fascinating and highly interesting for this group, even if you don't study locomotor control, because it honestly really beautifully combines principles of biomechanics and exercise physiology with neuroscience to give us kind of a more holistic kind of understanding of motor control and motor learning, which I think is kind of integral when we think about optimizing rehab interventions for neurological populations. So without further ado, I hope you'll join me in extending a hearty welcome, and I will turn the floor over to James.
All right, thank you, Amanda, for the introduction. Can you all still hear me clearly? Okay. All right, so I guess as you all are familiar with, we have a few introductory slides before getting into the meat of today's presentation. So we have a few objectives today, and I think it's nice to lay these out up front. So the majority of my talk, I'll be describing work that we've done to really understand what we call the cost and benefits of asymmetry during walking. And so we'll talk about some of this work in the context of walking in neurotypical individuals as well as people post-stroke. And then if time allows, I'll finish up with some of the recent work that we've done to develop VR-based interventions to improve mobility during overground walking. So let me just start my clock there. Okay, so as hopefully most of you can appreciate, mobility and specifically walking is one of the sort of fundamental features of human movement, and it's something that I think we often take for granted. But so I'm a parent with three small children, and you can see that within children that there's this connection, this connection between the joy that they experience and how fast they're moving. So their default is often running, and this is how they interact with each other. We often interact with our children in the same way. And of course, we also use walking as probably the primary means of moving through our environment, aside from riding and automobiles. And walking is often very fundamental for just many of the jobs that we have. And so for those of you with neuro backgrounds who don't study walking, you probably are familiar with the idea of spinal control of locomotion, and this idea that locomotion is really just this rhythmic activity. However, I think that's an oversimplification, and walking is actually a very challenging problem, particularly walking on 2 feet. And so, as bipedal creatures, we have to deal with the fact that generally during walking, we have just 1 foot on the ground. And so in some sense, we're always unstable, or we're always trying to prevent ourselves from falling. We also have this issue where we make what we call intermittent contact with the ground. And so, if I think about controlling my muscles and the forces they generate, the relationship between those forces and the resulting movements of my body change every time I make and break contact with the ground. And then finally, we have this issue where even if I can precisely control all my joint angles, that doesn't necessarily mean I'm going to stay upright, right? So you could imagine doing the exact walking motion that you would like, while being horizontal, right? So we don't actually have direct control over our body's orientation. And so we have to do this in a very strange way from a control perspective. And so this is a really challenging problem to solve. And so despite that, we know that we all generally will learn to walk fairly early, around 1 year of age, and we can eventually do things that are pretty impressive. So I always like to show this video to show the extremes of bipedal locomotion. And so this is someone, this is a skier who is showing us what he does for cross training. And you can see that he's able to move through, in this case, a range of environments, surfaces, all while primarily just using his 2 feet. And so this is, I would say the extreme end of what's possible with bipedalism, particularly for humans. Now, we all know that this sort of flexibility doesn't remain the case forever. And we can appreciate that when we have damage to the nervous system, such as what happens after a stroke, this often results in really marked mobility impairments. And so just as some things that we note for people post-stroke, they typically have less knee flexion when they are during the swing phase of gait. And when combined with the reduction in dorsiflexion at the ankle, this can lead to a tripping hazard. Similarly, we know that people post-stroke walk with gait asymmetries, where their right and left steps are of varying length. And they walk with a much higher energetic cost than neurotypical control individuals walking at the same speed. And one of the major challenges for mobility post-stroke is that people post-stroke often are at a much higher risk for falls than again neurotypical controls. And so a major question that we have in our field, in my lab specifically, is at what level should we think about intervening to improve mobility? And there's a sort of a question that comes even before this question, which is, what do we even mean when we talk about improving mobility? And so there are many different frameworks, of course, that we could use, but I really like to think about what we mean when we talk about improvements in the context of the ICF model, which many of you are familiar with. And so, I would say as a graduate student, and even throughout maybe a majority of my career, I think I sort of lived at this level, right? So we sort of think about any improvement at the level of something that we can measure in terms of body function or structure might be considered, to improve mobility. So we heard at the beginning that I'm an engineer by training, but I'm in a physical therapy department. And one of the things that I started to think about more, of course, being in PT, is more activity-based assessments of mobility. And so I think there's often, sometimes often an implicit assumption that changes at the body function and structure level will translate to the activity level, but that's of course not always true. And then finally, we can think about mobility at the participation level, which is beyond the work that we've been doing in our group, but is of course really important to consider. So I wanted to just sort of put the work that we've been doing over the past several years in the context of this model of what we think about when we talk about improvements in mobility. And so some of the work that I'll discuss looks at interactions within, I guess, a single level of this model. And so we ask, how do measures of body function and structure within the context of mobility? And so we'll be focusing on these 3 aspects highlighted here: gait asymmetry, as I mentioned early on, and how those asymmetries are related to balance impairments and metabolic cost. And this work will start with things that we've done in neurotypical individuals, and then I'll talk about how we've transitioned that to think about gait and mobility post-stroke. So in our lab, we study several different populations, but as I mentioned before, we're interested in understanding how people regulate symmetry during walking, how that affects energy cost and balance. And so these are ways that we think about the functional consequences of asymmetry. That's one second. Of course, we have this is lawn care day. So as many of you may appreciate or expect, we do a lot of this work in the context of what we call split belt or dual belt treadmill adaptation. And for personally, one of the reasons why I really like this experimental approach is that we can introduce people to a task that most people have never done before. Right? And so we can think about how people learn and what factors might be driving learning when we introduce them to this novel environment. Right? So I think about this as really a tool to understand that process. And one of the things that we do, so typically we'll have people walk on this treadmill with one belt moving faster than the other, and we measure several different aspects of their behavior, one of which is what we call step length. So for us on the treadmill, that's just the distance between the feet when the leading foot touches the ground. And so we can measure the step length when they touch down on the fast belt, compare that to the step length when they touch down on the slow belt. And so just to give you a visual sense of what happens during adaptation for those who haven't seen it. So this is, a lot of our studies, we collect full body motion capture because we're actually quite interested in what all of the body segments are doing during locomotion. And so this is a typical video of when people first are exposed to the treadmill. And so you can see that, of course, that they are walking with a very visible limp. However, after about 10 or 15 minutes of practice, we now see that their walking pattern is much smoother, and it's much more difficult to even recognize that one of the belts, in this case, is moving 3 times faster than the other. So over several, probably dozens of studies now over the past 15 or so years, what we know is that when people adapt to the treadmill, they eventually start by walking with steps of fairly unequal length. So you can see around the first vertical dashed line, that's when the belts first start moving at different speeds. And the white and black points here represent the step lengths on each belt. Okay. So the step lengths are initially quite different, gradually approach each other over time. Okay. So this is what we call a reduction in step length asymmetry. And we've also known that this reduction in asymmetry occurs with a reduction in metabolic cost. Okay. So these two things are, at least at that time, we knew that they were very much correlated. And so this raises the question of how is it that people reduce metabolic costs as they're adapting? And what should people do, right? So what is what we might call the optimal strategy in this environment? So one of the ways that we've explored this question, and you'll see this method come up through a lot of our studies, is that we like to use basically a form of biofeedback where we place markers on our participants and we give them this visual display in front of the treadmill, and we can ask them to match different step lengths on the right and left sides. So the bars that you see here, the black bar represents the step length on the right. And the left, the gray bar, represents the desired step length on the left. And so you can see by giving them feedback of bars of different lengths. You can modify their step length on their step length asymmetry. And so this measure of asymmetry is just the difference essentially between the right and left step lengths. And by doing this, we can determine the metabolic cost associated with different levels of step length asymmetry. In addition, we use a measure called mechanical work as another way to understand the energy cost of different walking patterns. So we won't necessarily get into all the details here, but if we look at just one leg across the gait cycle, we know that we can compute what we call the mechanical power performed by that leg or generated by that leg. And this is a function of essentially the ground reaction force and the speed of the treadmill. So when you first step on the treadmill, the leg is doing what we call a lot of generating negative power. In other words, it's absorbing energy. And we can think about that as sort of shock absorption. Whereas during the later phase, right before push-off, the legs are going to be generating positive power to accelerate the body. And we're particularly interested in the area under the positive part of this curve, which is referred to as our positive work. And so when muscles generate positive work, we know that this is this energetically costly form of muscle contraction when compared to, for instance, isometric force production or eccentric contractions. And so one hypothesis is that people are adapting such that they can reduce the positive work performed by the muscles in the legs. And so what we did in the study is that we can map the energetic cost of different levels of asymmetry. And so on the x-axis, we have our measure of step length asymmetry, where positive values correspond to taking longer steps on the fast belt. Negative values correspond to taking longer steps on the slow belt. And the y-axis here is what we call the work performed by the treadmill, essentially on the person. And so when the y-axis values are negative, we could basically think about that as the treadmill is extracting energy from the person, right? It's like walking on sand. Whereas when the y-axis is positive, the treadmill is actually essentially acting as an assistive device, right? It's performing work on the person, much like an exoskeleton. And so the prediction here would be that if the treadmill can provide assistance when there are positive asymmetries, maybe those asymmetries are less energetically costly. And so we can test that by first looking at the work performed by the legs, specifically the positive work. And what you can see is that this slope is negative, which says that at positive asymmetries, the legs are performing less work than they would at negative asymmetries. And so we think about this as people taking advantage of the work performed by the treadmill, such that the treadmill can essentially act as an assistive device when people walk with these positive asymmetries. And so that's mechanical work and asymmetry. What about metabolic cost? Well, we also observed that here I'm showing you the metabolic power on the x-axis and the positive work performed by the person on the y-axis. And we can see that as the positive work reduces, so going from top to bottom, there's also a reduction in metabolic costs, so moving from right to left. So this now demonstrates that, or suggests that positive asymmetries should require less energetic cost or have a lower metabolic cost than negative asymmetries. And that's indeed what we saw when we looked at the metabolic cost as a function of asymmetry. So again, to orient you, x-axis here again is back to our measure of asymmetry. The y-axis is metabolic cost. And this is a quadratic fit to the data. But the main point is that the minimum metabolic cost is observed at positive asymmetries. So if you're familiar with some of this literature, some of this might seem surprising because we typically have typically thought that the objective of adaptation is to adopt a symmetric gait pattern, specifically taking steps of and so the question then is, well, why don't, if the typical story is that people take steps of equal length at the end of adaptation, why is it that they don't have positive asymmetries, right? This is what you would predict if people were actually optimizing their gait to minimize metabolic cost. And so we explored this question recently, and one hypothesis was that people just didn't have sufficient time to adapt in previous work. And so to test that hypothesis, we actually allowed people to adapt for 45 minutes. So remember, a typical adaptation study is about 10 to 15 minutes. And so we are doing 3 to 4 times that length. So these are group data from this study. And here on the y-axis are our individual step lengths on the fast and slow belt in red and blue respectively. And so you can see here that if we stop our data collection at the duration of our typical studies, people have this, they take steps of equal length, right? So we would call this an asymmetry of 0. However, if we give them another 30 minutes on the treadmill, you see that they actually bypass this symmetry point. So they eventually learn to take longer steps on the fast belt, which is what we refer to as a positive asymmetry. And if we compare the work done at the end of the typical adaptation time to where they end up after 45 minutes, we can see that there is a continued reduction in positive work as they learn to adapt. And there's also a reduction in metabolic cost as they continue to adapt over these 45 minutes. So then getting back to sort of the major point here, this is really led us to sort of rethink a little bit the cost of asymmetry and sort of the goodness of symmetric walking during split belt adaptation. So now we're currently thinking about adaptation as this process of essentially energy optimization, where people are learning to use the work that the treadmill is performing so that they can reduce the energy cost of walking. And importantly, the optimal strategy to do so is to have steps of unequal length. So an asymmetric gait in this case is optimal. And this is also, we also know, or there's also evidence that having not just asymmetric step lengths, but asymmetric step times is also energetically optimal. And the last major take-home point from this work is that, there are lots of studies of adaptation and learning in different contexts, but we've demonstrated here, at least for walking, that the time course of adaptation, if we want to think about sort of a complete adaptation in some way, that time course is much longer than what people use or allow in typical experiments. Okay, so this is all the work done in essentially neurotypical young individuals, but how does this relate to populations that have asymmetries like people post-stroke? And so one general question is whether, when you look at someone post-stroke who's walking, and this is motion capture from one of our participants, is it possible then that maybe an asymmetric gait could be energy optimal for this population? And so to understand how we've been looking at energy cost and asymmetry post-stroke, I first want to introduce this sort of model that we have at the top here. And the details aren't critical right now, But the basic idea is that if I look at step length asymmetry on the left-hand side, in the previous study, we looked at the relationship between energy cost, metabolic cost, and step length asymmetry across a sample of, I believe this was 15 participants walking at different speeds. And we do see a potential relationship here between step length asymmetry and metabolic cost. Okay? But if you think about people's step length, the length of any one step is dependent both on how far you place the leading foot in front of the body and how far the trailing leg extends behind the body. And so we created this model that actually does what we call it, decomposes step length asymmetry into this foot placement contribution, as well as contributions that are more dependent on your step time and your speed. And so all of these things, so step length asymmetry, we don't really think about it as just a spatial measure, but there are temporal components of gait that also influence this metric. And so when we take that same sample and we look specifically at this foot placement asymmetry, we see a much stronger relationship than we did for step length asymmetry alone. And so this prediction suggests that perhaps modifying one of these two types of asymmetry could modify energy cost. And in general, I think there's again, often implicit assumption that reducing asymmetry post-stroke is beneficial, perhaps because it could lead to a reduction in the energy cost of walking. So we tested this hypothesis here using the same method that I described previously, where on the figure on the right here, we're just showing representative data from one participant, where the y-axis is their step length asymmetry, and the red and yellow are basically what they naturally do. Right? So if those two sets of data on average were 0, that would say that this person walks with a symmetric symmetric step lengths on average. But we see that there's a clear bias, so this person has a naturally asymmetric gait. In the green, we then give them visual feedback to try and equalize the step lengths. So we can see now on average, their step lengths are much more symmetric. So the question is, how does the energy cost change when we modify their asymmetry? So the take-home point is what you see at the top. We were actually surprised that when people reduced their step length asymmetry, there were no consistent changes in metabolic cost. So the panel on the left shows the asymmetry magnitude on the y-axis. And the three conditions, the first two conditions are basically their baseline asymmetry. And then the third condition is when we're asking them to walk with steps of equal length. And so what we can see is that in this symmetric condition at the end, they have a less asymmetric gait than during baseline. Okay, so they are reducing their asymmetry. However, when we looked at the metabolic cost across these three conditions, there was no difference in metabolic cost. So even though they're walking more symmetrically, there was no clear increase or decrease in metabolic cost. And this has also now been observed in a couple of other studies, also looking at the metabolic cost of changes in asymmetry in people post-stroke. However, if you'll remember what I showed you on the previous slide, we actually saw previously, we saw a stronger relationship between foot placement asymmetries and metabolic costs. And when we focused on foot placement asymmetries in this data set, we did now start to see a relationship between the change, the x-axis here is now basically the change in that foot placement asymmetry, and the y-axis, the change in the metabolic cost. And so for some people, we saw that there was an increase in metabolic cost, so that's the positive values on the y-axis, whereas for others, we saw a reduction. And so for us, this is really important because it points to the fact that it actually depends on the person's, well, first of all, um, obviously people post-stroke have different levels of asymmetry, and they have different levels of both spatial and temporal asymmetry. And these results suggest that how people reduce asymmetry matters. And so now we're really trying to understand, for a given person, is there a way that we could predict, a gait pattern, or what gait pattern might be energy optimal for that person? So that's some work we're doing in at the modeling and simulation level now, and we'll be doing moving into experiments later on. Okay. So yes.
Can I ask a question?
Sure.
Is there, if you go back to your previous graph, is there a difference? Is that difference in any way related to which leg is having a shorter stride, or because patients with stroke demonstrate this? Some of them have a shorter stride on the affected side, while some of them have a shorter stride on the unaffected side. Is that in any way related to that, or have you seen?
Excellent question. So let me give me 1 minute to think back on about this paper. I am almost positive. So we often test for that effect in our analysis, and I'm pretty sure we have that. We tested for that in this paper. I don't believe it came out to be significant. In other words, what we call the direction of asymmetry wasn't a significant predictor of the reduction in cost. But there are a couple of issues there. One is that you need a pretty large data set to try to disambiguate all of these features, because there are several features of their asymmetry. So we may have been underpowered in that respect. And is there another point? I guess that's the main point. So I'm pretty sure that we did not find it. We looked for it, but we may have been underpowered. But it's a really important point. And yeah, I don't have that data here, but we've been trying now to get a better understanding of why you see asymmetries in different directions in people post-stroke.
Thank you.
Can I ask a question also?
Yeah.
So I know that you're, or you said that you're using this sort of feedback approach to modify behavior, which is likely to be quite cognitively demanding. And so I was curious if you can separate out the motor cost of moving versus the cognitive cost of having to think about what's going on.
Yeah, so I didn't explain that well here, but here the yellow condition is what we call baseline plus feedback. So what we've tried to do is to say, okay, if we give you visual feedback that matches your baseline asymmetry, presumably that is adding the cognitive load from the feedback, right? So you're, looking at the screen, you're trying to match the targets, and yet your gait pattern should not be changing. So the idea is that is, it's not perfect, but it is that is just an added cognitive load. And here, if we look at the cost of transport, we see that there again was, no significant difference in metabolic cost when we added the feedback. But that's as good as we've done. You'd like to do the same thing for the condition where they are walking more symmetrically, but from there it's really difficult to get them to walk more symmetrically for a long enough period of time without visual feedback to measure the sort of metabolic cost. But yeah, this is as close as we've been able to get to trying to measure the energetic cost of the cognitive task, if that makes sense. Okay. So so far this work has really focused on energy cost, but we know that, or we don't know, we often assume that again, asymmetry may also be bad because it can impact negatively impact people's balance control. And so here again, there's always a measurement question for us in gait. What is it that we mean when we talk about balance control? This could be a sort of hour-long discussion in and of itself, but one of the measures that we've been using recently, which I personally like, is this idea of what we call whole body angular momentum. Okay, and so here the point is just that angular momentum is a measure where we again use full body motion capture, so we can measure what all the segments are doing. We can fit a model to these data using typical biomechanical methods, so that we can estimate what each individual segments, we can estimate each individual segment's kinematics. And momentum I like because it captures both the effect of velocity and inertia, or inertia is basically just mass distribution. Okay? And if we look at the angular momentum around the center of mass, this is telling us something about essentially how much effort or force would be necessary to arrest a fall if it happened. We also know that typically during walking, people keep this angular momentum, it's relatively low. And so one prediction or idea is that reducing angular momentum may be a way to, if we see a reduction in angular momentum, that may be indicative of improvements in balance control. And so again, what we're going to do is try to understand how changes in asymmetry impact this measure of what we call dynamic balance. So we're going to use the same kind of visual feedback here, but now when we think about measuring balance, one really important thing for us is that we think about what we call reactive control of balance. And really, this can only be assessed by perturbing people, or in some ways, like pushing them around a little bit. And so we do this by triggering what we call discrete perturbations. So as they're walking on the treadmill and performing this task, on random steps, we will just increase the treadmill speed. So that's this top figure for just one step. So we call that the perturbation step. And then when they lift the foot off the treadmill, we move the treadmill, we slow it back down to move back at its normal speed. Okay, so these are perturbations for a single step, and we can look at how long it takes for people to recover from these perturbations and how they affect angular momentum. And so in this figure here on the right, you see the black line represents the perturbation step. On the top, we're showing the belt speed. So you can see this increase in belt speed. And then the third row, where we show angular momentum, forward rotation. So if you're falling forward, by convention, that's represented as a negative angular momentum. And so if you compare the gray and the black line during the first half of the stride cycle, when we speed up the treadmill, accelerate the belt, we see that the angular momentum moves from being positive to negative. And that is representing this forward loss, light loss of balance triggered by the treadmill. And so the question is, does walking with an asymmetric gait affect how much people are perturbed in terms of their angular momentum? So again, we're going to give them visual feedback to walk with different levels of asymmetry. And the different colors here represent different levels of asymmetry. And the gray and open circles represent what happens when we trigger these perturbations. And the basic idea here is that we move them away from the target asymmetry, and over a couple steps, they come back. And so this is what the kind of raw asymmetry data look like. We then measure the effects of these perturbations by integrating angular momentum. And so in this case, negative values are representative of how much they are falling forward, right? So more negative values mean that people are perturbed more. And so we can see that during the perturbation step, people are falling forward quite a lot because of the unexpected acceleration. They then counteract that forward fall during the first recovery step, so that's R1. And then by the third step after the perturbation, they're sort of back to baseline. So these individual perturbations trigger multi-step recovery processes. And so the question in this study was, well, how does walking with asymmetric gait affect these are measures of angular momentum? And so here we're looking at, again, integrated momentum on the y-axis, and the different colors represent different levels of asymmetry. And what the main takeaway point from this figure is that there was again, this is neurotypical individuals with no baseline asymmetry. Regardless of the level of asymmetry, when we did these perturbations, there was no systematic change in angular momentum. So our conclusion, which was I mean, surprising to me at the time, I was expecting that as you walk with a more asymmetric gait, it would actually impair your balance. But that doesn't appear to be the case when we at least look at this measure of integrated angular momentum. And we have other work that has really explored this in sort of more depth to look at how people are coordinating movement among their segments. And it seems that the nervous system is really essentially allowing for variability in what we call segmental level control to maintain a consistent in whole body angular momentum. So it's a really interesting coordination problem that maybe we can talk about later for people who are interested. So now the question, so that was in again neurotypical individuals who don't have any baseline asymmetries. Now we can ask the same question for people post-stroke, where now, of course, our participants have a baseline asymmetry in both, how they in their sort of spatial temporal gait, strength, and ability to maintain balance on each limb. And so here we want to test I think the sort of general hypothesis that walking more symmetrically post-stroke may be beneficial for balance. And so to kind of understand what's going on here, first we want to look at here on the y-axis here is our measure of angular momentum. Again, this is in the sagittal plane. And we're going to look at this across the gait cycle. And so when we think about walking, we often think about it as this control sort of falling and recovery, right? And you see that here with the angular momentum. So at each foot strike, so where you move from, for instance, the paretic to non-paretic step, we see that our angular momentum is negative. And that's because this is the time when people are falling forward the most. And if we compare that level of angular momentum when they go from paretic leg to non-paretic and compare that to non-paretic to paretic, we see that people fall more when they are essentially in single limb stance on the paretic limb, right? So that's not all that surprising that they have less control. And so one question for us in this study was, if people change their asymmetry, how does this affect that peak momentum? In other words, are they going to fall more, less, or have no difference? And what we found was that as people, in this case on the x-axis, this is our change in step length asymmetry. So values that are negative correspond to reductions in asymmetry. Values that are positive correspond to increases in asymmetry. And then on the y-axis, we're looking at the change in that peak angular momentum. Okay. So positive values on the y-axis would mean that they are falling forward more than they did at baseline. And so, what we see here is that as people reduce asymmetry, they're actually falling forward more. In this, there are no perturbations in this case. This is just their baseline walking pattern. And so one of the things that this suggests, maybe let me take one step back here. So what we've demonstrated in these studies in our post-stroke participants, and what people have done in previous other studies before, is that just because people walk with an asymmetry, that doesn't mean that's the only way that they can walk, right? So these individuals retain the capacity to walk more symmetrically. And a big question is, well, why don't they? And this study points to perhaps the fact or the possibility that if people try to walk more symmetrically, it may actually lead to heightened instability. Right? So there's a balance component here that may lead people to adopt a more asymmetric gait. So this is something that we have a couple of more recent studies that also look at this effect when we add perturbations to people's gait. All right. So what time, really quick, just a time check, what time do you all typically finish?
At 1.
Okay. So, actually, just to have some time to talk. The last thing that I wanted to basically highlight was some of the work that we're doing to, move more towards thinking about the sort of activity level of the sort of ICF model. And the challenge here that we're addressing is when we think about conventional physical therapy, patients come into the clinic, they work with our PTs, and the goal is to do things in the clinic and perhaps with an at-home exercise program that lead to people being able to basically have increased participation, right? To be able to engage in activities that are meaningful in their environments. And so one of the challenges is sometimes it can be difficult to recreate the challenges that people face in the real world in a conventional clinical setting. And so a lot of our recent work has been trying to use or basically leveraging virtual reality to create environments that allow people to practice tasks that are more challenging and maybe more similar to things that they would face in the real world. And so I'll just highlight quickly, just talk a little bit about how we design these things, because I think it's kind of an important feature. So we are specifically what I'm most interested in, actually, let's mute this. So we have been using a system called the HTC Vive, which allows us to create environments where people can walk over ground in VR. And so a few years back, when we were starting to sort of play with this technology, we actually had no idea how to even design a task for overground walking. And so this just shows some initial games, or these aren't even really games, but ways that we were playing around to understand how do we add obstacles, how do we vary lighting and make things more challenging. And so here you can see we have this moving obstacle, and it naturally sort of triggers the participant to avoid it. So of course, visual stimuli are sort of very salient and lead you to sort of adopt obstacle avoidance strategies that you might use in the real world. And so this is the sort of fastest version of this, what we've done here, but we've now moved to a much more complex overground interventions. This is what we call Wordplay VR. And we're now able to, we have a task that has a sort of a large cognitive component where people are trying to solve a puzzle. So they're looking for in this case, our participant is spelling the word January. It's a New Year's related task. She has to go and find the letters. There's an avatar that's mapped to her body, so she also needs to avoid virtual obstacles. And one of the things that's really exciting for us about this is that, we have obstacle negotiation, problem solving, turning, reaching, squatting. And so we're now able to create a game-based environment that allows people to practice, you know, a lot of the tasks that they would find challenging in the real world. And for those of you who are maybe PTs, we've been tried to be really thoughtful about how the system is controlled. And this is a tablet-based user interface where you can choose different categories. So we wanted to make sure that this had what we call replayability. So if you can imagine working with maybe a patient doing this for several sessions, you'd like to have different categories of puzzles, different words. And the numbers here represent the level of challenge for each word. And that's based on essentially the number of letters and the frequency with which that word is used in English. So we have essentially several features that are now built into this application that allow for therapists to tailor the sort of training to the needs of their patient. So this is basically only done development here. We've done some usability testing, but we're looking to move forward into more sort of clinical assessment over the coming months. That was dramatically slowed by COVID. All right, so with that, the major take-home points, I'll kind of breeze through these so we can wrap up. You know, a lot of the work that we've classically done has been using the split belt treadmill to really understand learning. And now we're really thinking about using this device really as a sort of proxy or as a method to sort of parallel work that's done in the field of sort of assistive devices and exoskeletons, to learn principles by which people learn how to take advantage of external assistance during walking. We did work both at the level of metabolic cost and reactive control of balance. And we've shown what I think are some counterintuitive results related to the cost of asymmetry. And at least in healthy individuals, when we think about the balance related cost, you know, it seems to be indifferent to the level of asymmetry, which was really surprising to us. And we think that just the nervous system really cares about balance and is able to compensate for asymmetries when people's level of control is sort of completely intact. And then I showed some data where we looked at changes in asymmetry and how they impact energy costs and imbalance post-stroke. And one of the major take-home messages here, which we are still investigating on the balance side, is that these effects are going to be quite sensitive to the strategy that our post-stroke participants use to modify asymmetry. So this is something that we're really trying to, you can think about this as, you know, sort of getting a more personalized understanding of how changing an individual's gait will impact these measures of function that we think are important. So this is work that we're following up now. So many people to acknowledge a lot of the asymmetry work was done by Natalia Sanchez, who's a former postdoc in our lab and now current faculty member. And then a lot of our VR work was led by a now former PhD student, Aaron Kim, who is one of the people who will be moving to the East Coast and Hopkins in the next month. All right, so that's it. And I'll hang around for any questions you all may have. Thank you.
James, thank you very much for this. I mean, this really highlights the complexities that you see in rehab, that it's, you know, oftentimes we really focus on one particular piece. And what you see here is a real interaction of physiological, biomechanical, cognitive, and the neural constraints sort of imposed by the lesion. So thank you for the presentation. I want to ask a question about the balance part, right? So you showed that when people were more symmetric, they had a greater momentum, and that led to, so that is basically, you interpreted that as as poor balance, or not poor balance, but in order to be more stable they are being more asymmetric.
That's I would call it a working hypothesis. Yeah.
Okay, so do you think it is a compensation, or that in the sense that they do have the balance to control, um, and they have learned a way of walking that they're more comfortable with? And so is that a compensation that is a sustained one? Or is it that by training their balance, I might be able to get them to symmetry? So if there is a causal relationship, so I'm just kind of, I don't know the answer, but clinically that has a huge bearing on how do I really treat this person, right?
Yeah. Yeah. So we have thought about this, and in the paper, the way that we basically conclude is what our results are. This is single session and a sort of immediate change in people's asymmetry that they haven't really had time to practice. So to us, this says that if you imagine using a type of training that focuses on improving symmetry, that people may naturally be hesitant to it because it initially puts them in a place where their balance is more affected or more impaired. However, that doesn't necessarily mean that if they practice that symmetric pattern over an extended period of time, that their balance can't, that you can't improve both symmetry and balance. Okay. But these are things that we think are really important to test, and to not necessarily assume that symmetry is better because it looks more like what a neurotypical individual would do, but to measure changes at multiple levels, right? If I improve symmetry, does that lead to improvements in measures of function that I think are meaningful? So that's our overall framework.
Cool. Thank you so much. Great talk.
I was wondering if I could ask a question. I know we're a bit over, so I'm happy to do this offline if that's better as well. I think that your perturbation paradigm is really interesting and pretty cool. Particularly, you teased a little bit that there's maybe some flexibility with the intersegmental dynamics, or how the different solutions that the body's sort of willing to tolerate. And presumably there's some kind of range there where if you go outside of it, it's going to correct. And I'm just wondering, have you ever thought, or maybe you guys did this, have you thought about kind of taking a bit of an optimal feedback control approach to, or looking at it through that framework at all?
All right, so now I have to try to give the short answer to this question. Okay, so our general, one thing that we're trying to understand, right, so this is kind of a big grant that we're working on, is we're doing this in what we call an inverse method. So we would like to know it's inverse optimal control technically, but for a given person, can we actually determine what they care about? So that's one thing that we're really interested in right now. So a simple way to say that is like, what is your cost function? And specifically, we want to be able, the hypothesis is that people post-stroke are going to care about balance maybe much more than energy cost, whereas in neurotypical individuals, most of the weight is going to be on energy cost because their balance is fine. Right? So this is something that we're currently working on. In order to do that inverse problem, you still have to do you have to solve an optimal control problem. And we have, several different types of models where we can make predictions about what's energy optimal. And actually, I'll just show a little, I think I have a little tease of that. See if that's true. All right, so this is just a little cartoon here. So this model on the left is actually a mechanical simulation in MATLAB, a SimScape of a walking model on a split belt treadmill, where we said, what is, if we minimize positive work, right, which is what we think people care about, what is the gait that the model selects? And you can see that it's an asymmetric gait, and it takes the blue leg is on the faster belt. So it takes a longer step on the faster belt, which is consistent with what we see experimentally. We can use the model to now make predictions about what should happen at different levels of asymmetry, which is the little figure that you see on the right. So we and others, I think, have pretty decent methods to understand what should be energetically optimal. But when it comes to balance, it's wide open, because it's really hard to know how you assess. I mean, I talked about angular momentum, but there are many other ways that we could assess balance in the model. We don't even know how to represent like feedback control of balance during walking. So really excited. This is like, as a mechanical engineer, like I love this stuff. That's why I'm rambling right now, but it's really difficult problem to solve.
I have a meeting, but I hate to go. And also seeing some
Good to see
familiar
you.
faces like Lori and all in your pictures made me.
Yeah, I was wondering.
Bye.
All right, see you later.
Bye.
All right. Any other questions? No? Okay. I think we'll maybe end here. So thank you so much again, James. This was really great.
Thank you all.
Really
Good to see
fascinating
you.
stuff.
Yeah, thanks.